Hello, today we're going to look at this topic that says, does the representative volume element size matter when you're trying to do a microscale simulation involving a unidirectional composite? So this is what we're going to be looking at in this video to try and show you to run an investigation starting from a simple RVE size with just one fiber in it, which is the smallest size, onto the largest size. And we want to see if RVE size actually plays a role in terms of the effective properties that you determine things like Young's modulus and the strength of the composite. So typical result you get would be something like this that shows you RVE size definitely has an effect on the result with these different contour plots, and also even the stress strain data shows you actually there is an effect on RVE size. So let's go into the video and I'll show you how to do this. So the first thing is, what is the domain that we are looking at? So to the RVE with a square representation, so we've got these possible 6 sizes. So we select from this 6 to do a simulation. So starting from the very smallest, where you're looking at 30 by 30, and the fiber is just 20 micron in diameter, and then we go up to the one that is 180 by 180. What is the analysis framework? How are we going to go about doing this? So first, we're going to generate this representative volume fiber distribution using a software that I've developed. Again, please check on the cards for details about how to get hold of the software. It's called the MontCalGen, which is a short form for Monte Carlo generator. So this is a software that creates this distribution of fibers. And what it does is that it creates an output within MATLAB that looks like this. And this will be the domain that we're going to bring into ABAQUS. And within ABAQUS, we're going to run another software that I've developed for imposing periodic boundary condition, which is called the PBCGenLite. Again, look at the cast for details about the videos that I've made on this and how to get hold of the software. Please, for these two software, again, look at the description section of this video to see how to get hold of the software. All right, now from that, we create the ABAQUS representation, and then we run the simulation on it, and then ultimately we generate the stress strain plot. So based on this stress strain plot, we're going to then check whether actually the RVE size makes a difference in terms of unidirectional composites analysis. So what is the material we're going to deal with? It's a glass fiber reinforced composite, which properties are specified here, and I've taken that from a publication that I produced a few years ago on essentially some of these ideas I'm talking about today. The case studies that we'll be investigating here are uniaxial Y tensile deformation or X tensile deformation. So case 1 is 30 by 30, then we move to the 90 by 90, and then to the largest, which is 180 by 180. So let's go ahead and begin the modeling within ABAQUS. So here we are in ABAQUS, and how are we going to do this? So of course we can do it manually and go through the whole process in the normal way that we do it, but we're not going to do that. So we're going to use a script that I've written, a Python script that I've written. So if I show you here, so basically this is a Python script, series of Python scripts that I've written to help you, and I'll be providing these scripts within the with a link in the description section again for you to be able to download. So we're going to deal with the first, the 90 and the 180. So 30 by 30, the very first one. So I'll copy the link where that is, and then I'll run the script. So basically run the script, put the position where that information is, and then run the very first one. So that does, and then creates our domain for us. So we've got the domain written here. Okay, so why not let's do the same for the other bits. So we run the second script, which is in 91. The domain is created, and then we run the test script, which is a 180 case. So the domain are created. So if we look at them, you could see all the cases, they are all there. Now, within the domain, they are kind of very free. There is really not much. So I've made it so that you'll be able to specify whichever material properties that you want. So what we're going to do now is that we're going to go to the material library and create a library, a set of libraries for us to use. So I've already done this. So what do we need to do here? So if you go to the material library, click there. So you can create a brand new library, and then you add it to this domain. So as usual, you just create a library and then a material, and then you add it to the domain. So I already have my two materials created here, and they're basically available in the library. So how do we do that? So again, you populate this first one and then you add it to the library. But once you've added it, you do need to bring it into this environment, this particular model. So if you go to the first case, so this model is open, go to its material model, add this fiber. So you notice that it's already there. Add the matrix, it's already there. Okay, so if we go back and check, so you could see now we have the properties of the fiber and the properties of the matrix also specified. So we're not going to worry about that. So this is fine. So we'll do the same for the second case. So if we do the 90 case, right, then go to the material, select the fiber, add it to that 90 case, add it so they are already there. And then we'll do the same for the 180. So while this model is active, we go to the material, fiber added, matrix added. Okay, so we've got all three cases. Then we now do the section assignment for them, right? So double click on the section assignment. So we select the matrix. So that's our matrix. Select the fiber and make that the fiber. So that's done. Then we check if it is correct. So we've got it correctly set in the way it should be. So we can mesh this domain. So double click on that. So again, I'll select the three that is recommending for me. This is okay. Then select this. So what kind of shape, element shape, triangle is fine, and then mesh the domain. Okay, so that's the domain. It's all right. It's well presented. So what we can then do is we do the same for the other cases. So for this other case, again, do a section assignment, select the matrix, and select everything. Press down Control. Deselect the matrix, leaving the fiber behind. Then get the fiber. So it's in a normal place. We mesh as well. Okay, triangle is fine, and then you mesh the domain. So this is fine. Okay, now we look at the 180 case. Okay, so we could do a section assignment first. Select just the matrix first. So this is a matrix. Just press down Shift, deselect the matrix, leaving the fiber behind, and then that's fiber done. So we mesh them. Okay, select. Okay, so we mesh and everything is fine. So we've got the fiber mesh, we've got the matrix meshed. So all right, so we've got the three cases. Then if we go back here, so let's just walk our way through it. So we could then do, okay, our step is loading step. So this is fine. Our loading step is done. Within the matrix, so I'm going to create a set. So I'm going to call this a corner nodes. So select the nodes. I'm going to create this set based on nodes. So I'll select, press down Shift, select all the four corner nodes. We're going to use them to determine our stress strain plot. So then our history output, so corner nodes history. Okay. So now the set comes in corner nodes. So we're going to track a few things. So the first things are the displacements, X, Y, Z displacements, the reaction forces of those corner nodes, X, Y, Z reaction forces, and then their coordinate positions. Their coordinate positions, which is called chord. So chord 1, chord 2, chord 3. So these are the terms that we want to track and write to history that we're going to use later on for our simulation. So that's that. And then, okay, we could think about our boundary conditions. So X back roller, X back R, displacement. So I'm going to fix the back only in the X direction. So Y base roller. So I'm going to fix it in the Y direction. And then our displacement would be extension, loading history, and I'm going to apply it onto that point. All right, so now this is what we have, and we want to apply it on the x direction. Originally this size was 30, so if we do 20 or 30% of that, so let's do 30% of that, which gives us 9. Okay, so 30% of 30 is 9, right? So that's our displacement created effectively the way it should be. Boundary conditions all in place, loading history is accepted. So we can do the same for the other two cases quickly. Okay, so we have applied all the loading, the model details, the boundary conditions, the corner nodes, the history variables for the two remaining cases, the 90 and the 180. So we've also created the jobs for them. So what we're going to then do now is we're going to write this to input, select right click, write to input, select right click, write to input. So we've written the input variables of this to prepare it for the next stage. So if you now click here, set working directory, find where the working directory is, and then we're going to open that. So this is our working directory. So I'll select those three, which is where it's been written, cut them, then go back to where we wanted to be, which is in this. So there is a PBCGenLite workbench. So this is the code that I've written for accomplishing the second stage. So remember what we have done is we've used Monte Carlo to generate the domain in this form and brought that into ABAQUS, created all the boundary conditions. So we now need to move to the stage where we use PBCGenLite to apply periodic boundary condition and then run the simulation. Like I've been saying before, if you need this code, look in the description section, you'll see the link that gives you access to downloading the code. So let's just go ahead and continue doing this. Okay, so this is the environment, PBCGenLite, and we've got the three models that we need to apply periodic boundary condition. So we copy that link and then you open your MATLAB environment. So paste the link where PBCGen is located and make it the current working directory. So which is kind of what we have here. So we've got our code, we've got the three things we need. So we'll right click on this code, run, and then apply, select the first case, open. So this will run through to the end. And what it would then do is it would create the boundary conditions that we're interested in. So, and then give us some updates here about what is going on with the code. So first it says here it's read in nodes. The original RVE has all been done. Now the original file and the updated file. So a folder is created. Within this folder, we have the updated file. This updated file has a periodic boundary condition implemented in it. So what we're going to do is that we're going to just copy the link, right click, rename, copy that name. Now within ABAQUS, you can actually call, within MATLAB, you can call ABAQUS, okay? The command is exclamation sign ABAQUS lowercase ABAQUS job equals, so this is why I needed to copy the file name. So this is the name that we're looking for, and then you can do interactive. So you have to have ABAQUS somewhere in the system environment of your computer for this to run. So when you do this, so without having to leave ABAQUS, it calls up ABAQUS, runs the simulation, gives you a bit of the information, and then at the end it says the ABAQUS job has been completed. So you now know that it's completed. You've got the ODB file. So let's close this, clean the screen, and then go back to the folder where PBCGen is located, which is here. So we've done that of this case. So if we do the same for the second case, run, then we select the second case, open. Now it will do the same. It will apply all the boundary condition as required, apply all the periodic boundary condition as necessary. Okay, create a new folder, which is this folder. So we get into that environment. I'll right click as if I want to rename, copy that link, then put the same command ABAQUS job equals this interactive. So all being done within ABAQUS environment to get the model to run. So it loads up the ABAQUS environment. Within the code, it should have an idea within the keyword, the input file of what type of analysis engine that is required to do that. So it's kind of running through as you would do in ABAQUS, and then it's okay, it's finished, we're happy, so we can close the screen. So move away from that environment to do the third case, still within the PBCGen environment, GenLite environment, run. So we select the third case, open, So it's now read up to 2704, and then that's fine. We get into this environment, everything is done. Now we clear the screen, navigate to that environment where we've got that, and then again use our ABAQUS command, ABAQUS job equals, so we need to find the exact link, copy without the IMP at the end. Don't include the IMP at the end, interactive, because I want to see what it's doing as it's running. So again, it runs through to the end. It says it's found that I've got ABAQUS 2020 installed. So the licenses that it's using, depending, this is a license within my organization. And yeah, this is fine, 5 tokens within that environment. And then it's running the simulation, and it's using the ABAQUS standard to run it. So if you're using explicit, it will find that out and also do that. So, and at the base of here, you can see it says ABAQUS MATLAB is busy. And that is because it's trying to talk to ABAQUS to run the simulation, to do what it's supposed to do, and then it will finish and write the result. The other thing you'll notice that on the right hand side here, there is a lot of the results being computed, and then finally in the end, we've got all that done. All right, so we go back to PBCGen. So I've got the environment here. So what I'm going to do is here, I'll copy that link. Now I need to visualize the model. You can either visualize them directly from here if you want by saying ABAQUS viewer. Okay, but you need to bring in the exclamation at the beginning, ABAQUS viewer, and then supply the file name. So if we do that, so yes, it's okay. It will open up and then open just the viewer, the viewing environment of CAE, where you can look at your result and what you want. But that's not what we want to do. So we already have ABAQUS opened. So what I'm going to do is I'm going to go back to my original ABAQUS model, which is this environment. Now where I have all the original models. So what I'm going to do is just open the models that we have looked at. So let's look at the first case, the 30 case. So the ODB file of that. So if you double click, so you've got the ODB file. Okay. So this shows you the analysis that you need, the results that you generate, reduce the speed, and then turn it to plastic strain for a single fiber scenario, single fiber case. So let's look at the other cases. So if we move up here in the 90 case, okay, so single fiber case, no, multiple fiber now. So we can do the animation and see what's happening here. So the crack starts forming, and then you begin to get a more representative behavior of this composite due to the fact that we have, a bigger RVE size and everything looks interesting. So at the end, you can see the shape you generate. So let's do the third case, which is a 180 scenario. So again, the boundary conditions are all there. Plastic strain is incorporated, and then we could, increase the speed a bit. So you could see what's happening here. So again, we have periodicity implemented, and the domain are correctly in the way we should expect it to be. All right, so why not let's do a comparison. Okay, so we have all 3 cases, and you could see the differences in the simulation for all 3 of them, beginning from just the smallest case of 30 by 30 to 90 by 90 and 180 by 180. And the formation of the crack as it travels through them can be quite different. So there's actually little or no crack formed in the first case, some more cracks and a more stable simulation in the third case. So the RVE size is definitely playing a role in terms of these results. But what will really be interesting for us is to see quantitative data that can definitely help us establish whether this is actually the case or not. Okay, so how do we determine stress and strain plots? And this is again something I'd like you to look up. If you go and visit this book, this journal paper that I published, it explains it a little bit more. So basically what we want to try to do here is that this RV, this representative volume element that we're looking at, whether it's 2D or 3D, we are tracking displacement of nodes, node in the corners. So these ones in blue are the things that we're tracking their displacements. So node 3, node 1, node 4, and node 2. If it's a 4-sided, a 3-dimensional system, but clearly in this case, we only have 4 systems. So we could track all those nodes, record them in a variable, and then we use them to find our stress strain. And the formula to use basically is this formula. which means that the volume average stress for this RVE that represents what the whole domain would look like under the effect of these reaction forces would be 1 divided by the volume of the element that you're looking at, or the domain. So in this case, it will be the length, the width, and the height. If it's a 2D system, it will be the length and the height. The depth can be a unit of 1. So it will be a unit of 1 because it's a planar system. So 1 divided by the volume times the summation of all this. So what are all these? So this is a reaction vector, a line vector of coordinates of node 1. Coordinates of node 1. So that means the x coordinates and the y coordinates. If it's a three-dimensional system, it will be the x, y, z coordinates. So of node 1 times the reaction force in x, y, and z of node 1 plus vector x, y, z of node 2 times the reaction force on node 2. So this comes from the principle of virtual work that we're using here. So this is what we're going to do, and we're going to implement this within our model. So what do we do? So let's go back to analyzing what is happening here. So let's extract some of the properties. So if you click create X data, so X, Y data, so we already have some of the data, the coordinates from the corner nodes. So all the coordinates in the 1 and 2 direction, which are the X and Y directions. So we note that, press down Shift and hold that. And then now press down Control and select these ones individually. So that's all selected. So the coordinate positions, the reaction force, and the spatial displacement. Now go to Plugin Tools, Excel Utilities from current plot. So what we want to do is we want to export this current data into Excel. Hopefully you have Excel installed on your computer. So this is the resulting Excel data, okay, that we have. So what I'm going to do is I'm going to copy all, Control A to select all, Control C to copy. Now I've already produced a template, an Excel template, which I've called here analysis spreadsheet, which we'll be using for analyzing this data. So I'm going to just go right at the beginning at this corner and paste this new data that I've got. So what it has done is that it automatically plots the graph for me. Now I've given an indication of how these corner nodes are oriented. So node 1, node 2, node 3, and node 4. So that's what we're working with. And so we're extracting all the reaction forces, all the displacements, and the coordinate positions of all these nodes. And this is what we have here. So if you look very closely there, so the time data against the coordinate position of node 1 in the x direction, time data coordinate position node 2 in the x direction. So we'll do the same for the y direction for a 2D system. And then somewhere around here, you get the x-axis reaction force in for node 1, x-axis reaction force for node 2, node 3, node 4, and then we go on all the way. So why is that important? That is important because we need to utilize the idea of analysis of data from principle of virtual work, which I've explained previously. Okay, so here you see that I've provided some data on the force, the strain, and the stresses. So how do we determine all that? So the first thing we have to look here is what we've got on the force. And force basically was computed. So if I put this cursor here, so you see that the force was computed by utilizing all the data that we have in here. So for example, B6 times R6, so B6 times R6, so R6 is this. So the x coordinate position of node 1 in the x direction times the reaction force of node 1 in the x direction. So we move on to node 2, which is this D6. So the x coordinate position of node 2 times the force in node 2, and we run all the way through, add them all up in this dyadic multiplication of matrices. So we now have this data, and then I apply it across board, so we get that. And obviously what we have next here is basically using that force to divide by cross-sectional area. So again, if you study that script, you'll see how it's done. And then the same thing for strain. So how do we get strain? So strain basically here is calculated based on a displacement on the front face of the x-axis. Some cases you may have to use the back face or the other face. So the front face, the x2 divided by, so this is displacement data for node 2 divided by the original size of node 2. Okay, so this is what we have done. I've done here and applied that across both, so I've got my data for the displacement. Okay, for the displacement, and then you can now plot that. So I plot force against displacement, you get this data. Then right at the top here, so I've extracted a few things. The RVE that we've used, the Young's modulus is calculated based on the slope, the initial slope. So based on the initial slope of stress and strain data in the elastic region, and the second bit, which is the strength, is calculated based on the absolute maximum value of stress and the on the y-axis, which is the stress value term. So we've computed all that. So it gives you an indication of the data. So again, I've repeated that for the second cell, so you get a different result, and the third cell, so you get a different result. Okay, the third RVE size. Now I put them all together in a comparison plot, so extracting all the data just to give us an idea of what we have. And so what do we have here? So we've got a comparison of RVE size effects for effective properties for 1, 2, and 3. You can see that there is a little change in the modulus term. There's a slight change in the strength terms, but those are not significant. Those are not significant. And if you look very closely on this graph, so normal stress and strain, not much different in the elastic region and onset of yield. So there's not much difference. What is particularly important and different when the RVE size become important is what's happening in the post-yield response in this region. So clearly for the smaller RVE size, it's not capturing this significant stress softening that we see here. And even in the plateau stress, where everything kind of averages, it's not capturing, so it continues to decrease on and on and on. So there, clearly the energy dissipation for the RVE size is not as significant as you would expect for the bigger RVE size. So what's the implication of this? The implication of this is that the bigger your RVE size, the more you are able to capture not only the elastic response, but also the post-yield behavior of the unidirectional composites. So what would be a sizable RVE size? Then you need to do some series of studies to investigate that to come up with that conclusion. So the conclusion we can get here is that RVE size does matter. We can't just leave it off to chance, thinking that I can work with any RVE size. We need to do a systematic study, get to the RVE size where we start having a convergence of not only the elastic properties, but the post-yield response, as we can see in this data. So this is the objective of this video, and I believe I have established clearly RVE size matter, and we can see this in this result. So thank you for your interest in this channel. If this is the kind of content you like, please do subscribe to this channel. And if there is any part of the content that you like, please do click the like button so that the YouTube algorithm will continue to push this video to other people who may want to see it. Thank you very much. And all the spreadsheet I've used, the models that I've used, and the Python scripts will all be made available for you in the link in this video. So please do, get hold of that. Thank you, and catch you in the next video. Bye bye.